All right, so here we are continuing in section 3.1. This is the second video of section 3.1. And we are going to talk about exponential growth and decay. And you can see here up at the top, I have the definition for any exponential function. F of x equals a times b to the x. And any real number x, f of x plus 1 is equal to b times f of x. So what that's talking about really is from this previous page over here. Remember we did this right here. And we saw that whenever we added 1 to the x value, the x values are over here. We kept adding 1 each time. From -2 to -1, we added 1. Here from -1 to 0, we added 1. So every time we added 1 to the x value, that on this first one, we multiplied the y values by 2. And that number that we multiply by is our b value. So that's what that's talking about over here, where it says f of x plus 1 equals b times f of x. Now, as long as we have this a greater than 0 and b greater than 1, so a greater than 0, we want a to be positive here, and b is greater than 1. That function is increasing and is an exponential growth function, and the base b is its growth factor. So, for example, on the previous page over here, remember we found that f of x, see if I can scroll down here. Having some trouble. Here we go. We found that f of x was 3 times 2 to the x. So this is an example of a growth function because that base is greater than 1. If, however, the base is less than 1, like g of x, then it's an exponential decay function. So let's put those in over here. So an example of exponential growth would be f of x, we would have f of x is equal to 3 times 2 to the x, which is the growth function we came up with on the previous page. Then, if you want an example of the graph of that, let's think about what that graph would look like. Well, some of the values on that previous page, if you look back there, we had some values in our table. We had points like 0, 3. We had 1, 6. We had 2, 12, which would be, way up here somewhere. -1, 3 halves, -2, 3 fourths. And the graph would look something like this, and you can see that is a growth type of curve. So that's what an exponential growth curve would look like. So that decay function that we were looking at back on the previous page looked like this. Notice this base is less than 1, so that's going to be decay. If you notice some of the points back over on the other page, we had points like 0, 5, -1, 10, -2, 20. We had 1, 5 halves, so that's here, and 2, 5 fourths, so here. So when you have an exponential decay function, its graph is going to look like something like this. Now, notice on this that you have some features of the graphs that are the same. So for example, whether you have the exponential decay or back here on the previous page, the exponential growth function, they both have the x-axis as an asymptote. They both have domain, all real numbers. They both have range, 0 to infinity. They're both bounded below. You know, the only difference is this exponential growth is an increasing curve, whereas exponential decay is decreasing. Now, just like we did for all the functions that we have studied, we need to be very familiar with how to transform the graphs. So let's look at that here on this slide. So in this first graph, in all of these, we're describing how to transform the graph of f of x equals 2 to the x into the graphs of the given functions. So first, let's just draw y equals 2 to the x. That has values like 0, 1. If you just think about a chart, an XY chart, when x is 0, 2 to the 0 would be equal to 1. If you had x is 1, 2 to the first is 2. So those are two good points right there, 0, 1, and 1, 2. And we know that that's an exponential growth curve, so it's going to look something like that. Now, if you have this x plus 1 up here, you may remember adding 1 to the x value just shifts it left 1 unit. So all you're looking at there is taking this graph, shifting it to the left 1. So each of these points goes 1 to the left, and now, you know, your graph looks something like this. If you look at B, which I think I have on the next page here, 2 to the negative x, that's when you multiply the x by a negative, that just reflects it across the y-axis. So instead of having your basic 2 to the x, which looks like this, now you're looking at 2 to the negative x, which would be like this then. Reflecting across the y-axis. Remember, if the negative is out front, that's where it reflects it over the x-axis. Okay, moving down here, we have k of x equals 4 times 2 to the x. What that does to the graph is it stretches it vertically by a factor of 4. Whoops. Okay, so your original graph went through the point here, you know, your basic point 0, 1. Now that y value is going to be multiplied by 4, so it's now going to go through up here at 0, 4. Instead of going through the point 1, 2, we are looking at the point 1, 8. And this graph is a little bit sloppy, I apologize, but you get the idea there, I think. So you're just stretching vertically by a factor of 4. All right, next we want to look at the natural base e. I know you all have heard of e before, you studied it last year, but here is an official definition of e. You may not have seen that before. It is the limit as x approaches infinity of the quantity 1 plus 1 over x to the x power. Now, that may seem kind of strange, but let's look over here at this graph that I made for you. In this first function here that's in red, this is the graph of y equals 1 plus 1 over x to the x power, that first function you see there. As you can see, you know, it has a couple of asymptotes, one of which is this blue line here, y equals E. Now, that line, as you can see, this red graph, the further out we go on the red graph, the closer and closer we get to that blue line, which is y equals E. And remember, over here you can see that E is approximately, here's the value, 2.718. So the further out you go on this red graph, the closer and closer you get to the 2.718. And if I were to scroll out this way, you can see that you're getting even closer and closer. So that just kind of illustrates this definition that you see here of E. So any exponential function that we've been studying here can also be rewritten in base E. So it can be rewritten as f of x equals a times e to the kx if you find an appropriate value for that constant k. If you have f of x equals a times e to the kx, it will be an exponential growth function if a and k are both greater than 0. It'll be an exponential decay if a and k are both less than 0. So an example of an exponential growth would maybe be something like f of x equals, equals 2 times e to the 1.3x. Okay, so that's an exponential growth because a, this first term here is greater than 0, and k, which is the coefficient of x, that's also greater than 0. An exponential decay would be something like f of x equals e to the negative 0.375x. Okay, that's an example of exponential decay. There, the a value is actually 1, and then the k is less than 0, so that's what makes it into a decay function. Now, on your sheet there, in your notes, it also gives you a place to write this. This is not something we're really going to use. It's just sort of an interesting fact that E can also be written as this infinite series, which is sort of surprising. And remember, factorial just means, like if I have 4 factorial, that means 4 times 3 times 2 times 1. 3 factorial means 3 times 2 times 1. If you add up infinitely many terms of this series, it will equal E, which, again, we're not really going to use that. It's just kind of an interesting fact there. Okay, real quick, let's go over to our next page here. And this is talking about transforming the graphs of f of x equals e to the x. Now, if you're graphing f of x equals e to the x, again, think about that XY chart. You know, again, if x is 0, e to the 0 is still going to be 1, so it's still going to have that anchor point at 0, 1. And then before, when we were doing 2 to the x, we had the point 1, 2. Here we have the point 1, e. Remember, e is about 2.718. So it's somewhere around in here, 1, 2.7-ish. So here's your regular e to the x. And then remember, if you are multiplying that x value by -2, what that does to the graph, the negative is going to reflect it across the y-axis. And then the 2 is a horizontal shrink by a factor of 2. So when you graph that, you know, reflect it and horizontally shrink it a little bit, it would still go through this point 0, 1, but it would be horizontally shrunk there a little bit. Okay, I'm going to have to stop right there for my 15-minute time limit. So next video, we'll pick up where we left off.